Hello and welcome. My name is Aryan Rezai Rad, and I'm a postdoctoral researcher at the Laboratory for Timber Construction at EPFL, as well as the National Center of Competence in Research, NCCR Digital Fabrication, located at ETH Zurich. My colleague Nicolas Rogeau in the previous video talked about the general design workflow associated with timber plate structures with wood-wood connections or integral mechanical attachments. And in this video, specifically, I'm going to talk about finite element analysis associated with such a structural system using the previous case study that Nicola just explained.
But before diving into details and talking about the detailed simulation process associated with these kind of structures, let me give you a very brief introduction about the simulation-based science and numerical simulations, basically, and computer modeling in timber, or let's say in general in plate or shell structural systems. The numerical simulation of structural components with plate or shell action typically lie along the spectrum of complexity. Specifically, the use of 3D brick elements with contact zones can be considered at one of the ends of this spectrum, one of the extremes, while using 2D continuum shell-based elements or the use of only spring and beam elements as macro models can be considered as the other parts of this spectrum. So in order to simulate our structural system, today we use an open source computational platform for research and collaboration in engineering, architecture, and construction, which is referred to as COMPASS. COMPASS is an open source framework originally developed at the Block Research Group at the National Center of Competence in Research, NCCR Digital Fabrication. COMPASS consists of different libraries and components that enables researchers, engineers, architects, and also construction sectors to deal with geometry processing, robotics, CAD, computer-aided design, computer-aided engineering, mesh processing, etc., etc. For example, in our case, we're gonna today talk about one of the extensions of COMPASS framework, which is COMPASS finite element. So COMPASS finite element extension is basically consists of two main domains, model and problem, which are kind of integrated during the simulation process. It means that while simulating your structure inside of COMPASS FEA, you're explicitly modeling material section, nodes, element properties, associated elements, and also interactions if you're working with 3D finite element models, while you're also taking into consideration the design steps like the loading and boundary conditions or other constraints that you might have in your project. And this, which is explicitly and directly simulated and used inside the CAD environment, such as, for example, Rhinoceros or Blender, it can be read by the backend, the finite element solver, such as Abaqus, OpenSys, and ANSYS. So in our case today, we are gonna work with Abaqus is one of the backends which is quite well developed in COMPASS FEA 1. That's let's say one of the first generation of a finite element extension inside of the COMPASS framework. And by using Abaqus, we aim to define not only our model but also the problem, the analysis, the solving algorithm, and all the rest of the algorithms required to simulate the structure. In order to simulate our structures or timber plates with wood-wood connections, basically two main considerations or assumptions are made. The first assumption is to consider that each timber plate is simulated using a shell element, and that shell element is based on a mesh and constant cross-section with an isotropic material, because our timber in this case will be a plywood with 50% along fiber parallel and fiber perpendicular directions. And also the connections are simulated using only spring elements with 6 degrees of freedom. The mechanical properties of 4 degrees of freedom out of those 6 degrees of freedom are experimentally derived. And as you see here, for example, for tensile, edgewise, flatwise, and flexural behavior of those wood-wood connections, we've already carried out a couple of experimental studies. We determined the load deflection or moment rotation behavior of those connections, and then assigned those properties into the equivalent spring models that you see here in this slide. Or alternatively, we can simply just define the dimension of the wood-wood connection. Specifically, I'm talking about this area here, and simulate this area as a simple beam element in our structural model. Now, before talking about the design workflow and the procedure we already kind of explained generally, I would like to just give a very brief introduction about Compass and Compass FEA environment, how you can get access to Compass database, and how you can install Compass FEA very briefly. So here you see the Compass homepage where you can find the documents, extensions, examples, and if you want to contribute as developer, you can also have access to the repositories through this website. So in the Compass extension, you can find the different extensions available for Compass, and here for let's say the engineering extensions, you can find Compass FEA and Compass FEA 2. Currently, Compass FEA 2 is under development, and feel free to visit this website for further updates. For Compass FEA, how to install Compass FEA inside your environment, the tutorials, examples, and also having access to the API, application programming interface. You can find all of the information here. So now that you see that all the documentations are kind of ready to use, and given this consideration, now we can go through the grasshopper and rhinoceros environment, and I can talk a bit about the design steps required for finite element simulations of timber plate structures. Here is a geometry that Manis generated, and I believe in the previous video, my colleague Nicola already described the different modules. And that geometry will basically serve for further finite element analysis. If I want to reiterate that I explained in my previous slides, we need mid-contour polylines and also line elements in order to represent shell elements and connections respectively. So in order to show that, here it's what Manis generates with respect to finite element analysis. It consists of mid-contour polylines as well as beam elements in order to represent connections. So now we use this geometry in order to generate mesh required for finite element analysis. For that to happen, we are using a tri-mesh grasshopper component written and developed by Daniel Piker. In Grasshopper, I would recommend to use the latest version of Grasshopper. And here it's basically if I want to just zoom it in here, it's the overall geometry of the mesh, including the surface elements for timber plates as well as connections. So as I already explained in my previous slides, one of the required steps for finite element simulation is to define boundary conditions and loads. Here in the Grasshopper environment, we've already used some Grasshopper components in order to isolate those points and those areas in our domain, in our structural system, in order to define boundary conditions and also loading points. So far, we already talked about the input geometry required for finite element analysis, such as mesh for timber plates and beam elements in order to represent connections. And also now what we need to have here is to define non-geometrical or mechanical properties for the finite element procedure or other simulation requirements, such as defining the type of the support that can be pin-ended or fixed supports, and other design properties. And given this into consideration, I will now go through the finite element code we developed using Compass FEA1, and I will explain that to you. So here it's the code we developed for finite element analysis. As you see, it is heavily depending on the libraries defined in Compass and Compass FEA, including Compass FEA structure, Compass FEA cat, Compass core Compass library, Compass geometry. And these libraries are used in order to define the grasshopper component that we've already developed inside Manus for structural analysis. So we are actually importing the geometry and using some kind of vector calculations in order to identify the local coordinate system and global coordinate system of our structural components, shell elements, and specifically our linear elements. In addition, we would like to define, first of all, the mechanical properties of our structural element, which would be elastic isotropic, because we are assuming that timber plates here are plywood with a 50% distribution of fiber veneers along fiber parallel and 50% along fiber perpendicular directions. And then in the next step, as I've already mentioned, we would like to define the type of our boundary. Boundary conditions can be either fixed or pinned according to the construction constraints and limitations, which can be easily defined here in our grasshopper component. Then, of course, defining again what I've already mentioned regarding the point loads as well, or defining the shell elements by actually identifying a shell section or rectangular section in that case to simulate the wood connections, the IMA, and then all of it will be translated into an input file to be introduced to either Abacus, OpenSeas, or other backends. So let me go through the code. So in the very beginning, these are the functions defined for the development and for building the grasshopper component. And then next here is the block of the code used for generation of the finite element analysis and building the model. So basically, Compass finite element extension operates in Rhino, and to do that, first we bake the geometry that was generated by Grasshopper in order to be used for further assignments and analysis, which are already shown here. Then for the very first step, we define the local coordinate system per each linear element, so that the local x prime, y prime, and z prime local axes are defined. And then by that, we will be able to identify the width, length, and height of each local IMA, integral mechanical attachment. Then what we do first is to basically generate a structure that all of our data, all of the information required, like mechanical properties and geometrical properties, or the assumptions will be used to solve the stiffness matrix or the inversion, etc., will be stored in data structure. The next step is to define elements here. As I previously mentioned, elements are divided into two categories: shell elements and beam elements. Now we are defining two sets of nodes. The first set is actually loading points that will be applied to the top of the structure, and also supports or boundary conditions at the two sides of those 3x3 9 boxes that you saw. The next step will be defining the material. We are using elastic isotropic materials for both shell elements and beam elements here. However, the dimension or the geometrical properties of these two categories are different, as you can see here. So basically, for shell sections, we use a rectangular plate section. This is generally defined in Abacus as a section plate. And for beam elements, for connections, we use a rectangular section in order to define the the mechanical properties of link elements or for Wood-Wood connections. Okay, now by having both geometrical and mechanical properties of shells and connections, we assign those two categories into already baked layers. And then, given that our support conditions can be either fixed or pinned, we assign each of these properties into the associated nodes that we've already defined. We assign point loads by using point load command in Compass FEA1 that would assign automatically the direction and also the amount of load per each node. Then now it's a time for defining the steps, the analysis steps. For example, here we just apply the boundary conditions, load, and then carrying out an analysis. However, one can define like eigenvalue analysis or dynamic analysis to get, for example, the period of the structure, the frequency, or applying not static analysis but dynamic solving algorithms to the domain. Then at the very end, we just define what kind of outputs we want from our model, like von Mises stress or principal stress or forces in the support area, the direction of forces at the support area, and other parameters which can be different from one project to another. Another important point here is that now, for example, we define Abacus as our solver, as our backend, but that can be changed into other solvers like OpenSeas or like ANSYS in that case. But today we're just going to talk about, let's say we're just going to presenting the Abacus as our solver today. And then here are some outputs. We are using RhinoPlot or RhinoPlot comment regarding plotting those data in our Rhino environment. Now, actually, we have all of the components required for a valid finite element model ready, and now we can get back to Rhino and show the results. So now, as you can see, here are the required geometry for finite element analysis, like the boundary conditions in the left side or the right side of our structure, the point loads applied at the top of the structure here, meshes and connections here, plus geometrical and mechanical properties like the width and thickness of connections, the module of elasticity, Poisson ratio, loads, unit loads applied to each point according to the ultimate limit state of the structure. And then maybe I can now show you the vertical displacement of the structure, which corresponds to almost 1.2 millimeter. This is an exaggerated file, so in order to show the deflection of our structure, and the maximum displacement happens in this corner because this is a non-restricted edge. And then maybe in the next step I can show you the direction of the forces for each of restrained boundary conditions. The magnitude is also kind of represented here by the size of the arrow and the color. Also, here you see, we would just like to reiterate the direction and the magnitude of uniform loads applied at the top of the structure. And maybe one of the most important parameters is von Mises stress, the stress in both plates and connections here. And as you see, the amount of stress concentrated around connections are very well pronounced, and that means that the structural performance of such systems is mainly governed by the behavior of connections. And the total amount of stress here was around 6.2 Newton per square millimeter, 6.2 megapascal. So that's pretty much it from my side, and I hope that in this video you've gained insight into the global mechanism of finite element analysis inside of Manis and how Manis is linked to other computational platforms such as Compass and Compass FEA for engineering analysis. And I would like to thank you very much for your attention and following us. And until the next video, goodbye.